So, do you have any question or any doubt? Do you have any question or doubt about the topics that we discussed in the last class? So,
No, ma'am.
should I start from here? So this is
Yes.
to some extent illegible, section 1.3, and the uh, heading of the section is locations of the roots of the characteristic equation on S plane and the stability of the system. So from the name itself, it's clear that the stability of a linear system actually depends upon the locations of the roots of the characteristic equation. Now, I guess you know what is meant by characteristic equation. What is known by characteristic equation?
Yes, ma'am.
Okay. So let's assume, and for the time being, intuitively we can argue that the stability of a linear system doesn't depend upon the nature of the input given to the system. Why intuitively we are going for this particular assumption? Because just consider the examples that we have discussed. So what we did, we impress some disturbing force on a system, and after that we remove the force. Okay, and after removal of the force we are trying to find out the nature of the response generated by the system, and we are trying to find out whether the response, as time progresses, response increases without bound, or the response term dies down to zero, or the response term becomes a constant or constant amplitude oscillation, right? So we are trying to find out the nature of the response terms after removal of the input, number one. Number two, think of that particular system where we took several troughs on which a ball was resting under the force of gravity, right? So there we discussed that uh, we gave a just mild push. That means the disturbing force was a kind of impulse, isn't it? And instead of that, just consider that we are going on pushing the ball. And after a while, we are removing that particular, or we are stopping to push the ball further. In that particular situation, also, the ball will describe a different trajectory, but will finally come to the position of the rest in case of asymptotically stable systems. And for non-asymptotically stable system, the ball will finally come to rest, but the position may not be the, or in most of the cases the position will not be the original position, right? So in this particular case, when we are pushing the ball for a while, the disturbing input is of the nature of a step input, isn't it? But just we if we consider those two examples, or that particular example, then we can conclude that be it impulse kind of a disturbing force, or be it a step kind of a disturbing force, or even if we can think about ramp kind of disturbing force, the stability of the system is not changing. Hence we conclude that the stability of a linear system doesn't depend upon the nature of the input. There is one exception that we'll discuss or we'll study later on. So, for our convenience, what we are assuming here, we are assuming that the disturbing force is of nature of unit impulse. Why? Because we know that the Laplace transform of unit impulse is 1. So the closed loop transfer function, I guess you know what is the difference between open loop transfer function and closed loop transfer function.
Yes, ma'am.
Okay, so where CDS is the output response generated by the system because of the input applied to the system, which is the reference input RS. So CDS by RS is equal to TS, where TS is the closed loop transfer function of the system, right? So CDS, we have already discussed what is going to be the nature of CDT, right? So from this, CDS is TS into RS, and since the input is taken as unit impulse, so RS will be equal to 1. So CDS will be equal to TS, and after taking the Laplace inverse, the time response, we are interested about the time response, output time domain nature of the output response, that means CDT. And finally we'll try to find out limit t tends to infinity, CDT is equal to, what is CDT, what is the nature of CDT. That means we can put a question mark over here. So let us now consider an nth order system. So nth order system means the transfer function can be expressed. If you want to scribble some extra information, you can do that. So if you want some time for that, you can stop me. Should I continue?
Yes, ma'am.
Okay. So we are considering an nth order system. Now this transfer function can be represented as the ratio of two polynomials, and the polynomials will be functions of S, where S is the complex frequency, as you know. That means some PS divided by QS, right? And the denominator polynomial QS is known as the characteristic polynomial of the system. Clear? The characteristic polynomial of the system, denominator polynomial. And if we equate that to 0, that means if QS is equal to 0, then we'll get a characteristic equation. We'll get an equation, and that is known as characteristic equation, right? And for an nth order system, the characteristic polynomial or the characteristic equation will be of the order of n. That means if you solve the characteristic equation, then will characteristic equation is obviously a function of the complex frequency S, and we'll get n number of the roots of that particular equation. Also, I guess you know that this n number of roots of the characteristic equation are the closed loop poles of the system. Remember, the closed loop poles, not the open loop poles. Okay, the closed loop poles of the system, right? So for an nth order system, the system will have n number of closed loop poles, or the characteristic equation of an nth order system will have solutions, n number of solutions, and those n number of solutions are obviously the roots of the characteristic equation. Now also we know that the roots of a characteristic equation, the roots of a characteristic equation can be real, can be complex conjugate, right? Or can be combination of these two, real as well as complex conjugate. And moreover, the roots may be simple, or roots can have some order of multiplicity. Order of multiplicity means at one particular location on S plane, just think about S plane. Since I don't have a board, I can draw the S plane. So can you follow the cursor? So can you follow the cursor?
Yes.
So suppose these are the two axes. Here we plot sigma and this is j omega. So this plane will give us the S plane. And since QS is function of S, hence the roots of the characteristic equations will be located on this S plane, this particular S plane, right? And if a root occurs on the real axis, positive real axis or negative real axis, then the root will be called a real root. And if a conjugate part is there, complex part is there, then the roots will occur in conjugate pair. So those roots will be called complex conjugate roots, or roots can occur on the imaginary axis, right? And suppose a real root at s equal to say some sigma, either over here or over here, if two roots occur at the same location, s equal to some sigma 1, two roots occur at the same location, then we say that the roots are of order 2. That means the multiplicity of the root is equal to 2, isn't it? I guess you know this. Yes or no?
Please repeat.
Roots of
Yes,
multiplicity.
ma'am.
Roots of multiplicity.
Yes, ma'am.
Hmm? So if suppose a single root appears on the S-plane at S equal to some sigma 1, a single root, then we call that root as a simple root, or the order of multiplicity will be equal to 1. It might so happen that, think of a critically damped system, it might so happen that two roots are occurring at the same location on the S plane. At S equal to some sigma 1, two roots are occurring, right? That means at S equal to sigma 1, double roots are there. Can you
Yes.
follow? Hmm? Double roots are there. So in that case, we say that the roots have a multiplicity of the order of 2. At s equal to sigma 1, if three roots appear, then we say it can appear. Okay. So in that case, we say that the roots are of the order of multiplicity, which is equal to 3. Clear? Just think of a
Okay.
transfer function, very simple one. You can write it down. A by s cube. A by s cube. So at s equal to 0, that means at the origin of the s plane, at the origin of the s plane, three roots are appearing. The system has three roots at the origin of the s plane, isn't it? A by s cube, if that be the transfer function of the system.
Yes.
So in that case, we say that at s equal to 0, or at the origin of the s plane, the system has three roots, hence the roots are having an order of multiplicity which is equal to 3.
Okay, ma'am.
Okay. Similarly, think of another transfer function, say a by s plus sigma 1 within bracket, whole within bracket, a by s plus sigma 1 within bracket to the power say k. That means on the s plane at s is equal to sigma 1 on the real axis, at s equal to sigma 1, at that particular location, k number of roots are there. Now is it clear?
Yes, ma'am.
So we say that at s is equal to sigma 1, k, the system is having k number of roots. That means at s is equal to sigma 1, we are getting A real root with order of multiplicity is equal to k. So we can have this kind of transfer functions. That means we can have real root as well as complex conjugate roots with different order of multiplicity.
Okay.
So now so note that closed loop poles of a system are same as the roots of the characteristic equation. So now let's come to this particular equation. So the closed loop transfer function, as I said, is basically the ratio of two polynomials which are functions of S, complex frequency Ps and Qs. And for nth order system, the Qs, I'll follow this particular convention. Throughout this course, I'll follow this particular convention. The QS can be written as I said, the QS will be an nth order polynomial. So A0 s to the power n plus A1 s to the power n minus 1, right? Plus a n minus 1 s plus a n. How to remember this particular convention? If you add this to always s to the power n and the suffix of the coefficient. So for this term n plus 0, so that is n. Here n minus 1 plus 1, that is n, right? Here n minus 1 and s to the power 1. That is, if I add this two, I'll get n. So I'll follow this particular convention. In some books, you may find that the polynomial is written in this form: a n s to the power n, a n minus 1 s to the power n minus 1, so on and so forth. But I'll follow this particular convention. So this will be, QS will be an nth order polynomial and it will be in the denominator. This is the closed loop transfer function. And PS will give us, if I solve PS equal to 0, then I'll get the locations of the closed loop zeros of the system. Try to recollect what you have studied in system theory. So if I solve this particular polynomial, PS is equal to 0, then I'll get the locations of the closed loop zeros of the system on the S plane, yes or no?
Yes.
Yes, ma'am.
So let's assume that the system has m number of closed loop zeros. So in that case, PS will be a polynomial having an order which is equal to m. So the polynomial can be expressed in this form: b0 s to the power m plus b1 s to the power m minus 1 plus bm minus 1 s plus bm. So is the convention clear? So henceforth, instead of CDS, we'll consider just, we'll drop the suffix d and we'll write it, the closed loop transfer function, as CS by RS. CS by RS. So QS, as I said, is the characteristic polynomial, you know, and QS is equal to 0 is the characteristic equation. And if you solve the characteristic equation, we'll get a number of roots of the characteristic equations and or the locations of the n number of closed loop poles of the system on the S plane. On the S plane. So next, what we'll try to do, our objective is to find out our objective is to map the locations of the closed loop poles of the system or roots of the characteristic equation of the system on the S plane and the response term they contribute, they generate at the output of the system. Should I repeat? Should I repeat?
Yes, ma'am.
So now we'll try to what was our basic premise? Our basic premise was the stability of a linear system depends upon the locations of the closed loop poles of the system or roots of the characteristic of the system on the S plane, right? That was our basic premise. The stability of a linear system depends upon the locations of the closed loop poles or roots of the characteristic equation of the system on the S plane. So now to establish that particular claim, now we'll try to map the relationship between the location or locations of the roots of the characteristic equation on the S plane and the response term they contribute. Okay, now it will be clear. So from this equation, this is very straightforward. So if we want to find out the locations of the closed loop poles or roots of the equations on the S plane, then we'll have to solve this equation Q is equal to 0, right? That means we'll have to find out the roots of the characteristic equation. We'll have to solve this equation for a number of roots. Okay, so since this is PS by QS, so if you go for partial fraction, then we'll get the roots of the characteristic equation. Now, just take this example. CS by RS, that is the closed loop transfer function of the system. Let's assume it's a very simple one, that is A by S minus sigma. Okay. For the time being, we are not concerned about the sign of sigma. So if this be the transfer function, then CT, since RS is unit impulse, hence it will be 1. So CS will be A into S minus sigma. So CT, we want to find out the response term generated by this root, which is located at S equal to sigma, by this root of the characteristic equation. Okay, so the response term contributed by this root or response term generated by this root will be Ct equal to A into e to the power sigma t. Yes or no? So if the root
Yes,
is
ma'am.
located on the S plane, if the root is located at S equal to sigma, then the response term contributed by this simple real root will be A into e to the power sigma t. So likewise, we'll consider different kind of location, different types of locations of the roots of the possible locations of the roots of the possible locations of the roots of the characteristic equation on the S plane. And after that, we'll try to find out or try to answer this question. That is CDT, what will be the nature of CDT or CT as t tends to infinity. And the answer to this question will give us the answer to the stability of the system. So let's consider the following table. So two columns are there. The first column is type of roots. That means locations of the roots of the characteristic equation on the S plane. On the S plane. Types of roots means locations of the roots of the characteristic equations on the S plane, or locations of the closed loop poles of the system on S plane. And in this column, we'll try to find out the nature of the response terms contributed by those roots. So let's start with very simple one. The first possibility is single root or simple root. That means root which doesn't have any multiplicity. Single root at is equal to sigma. Already we have seen that the response term contributed by this simple root, which is located at s equal to sigma on the S plane, is a e to the power sigma t, that we have seen.
Yes, ma'am.
Okay, now we are considering roots of multiplicity k at is equal to sigma. So to make it simple, just write down the transfer function, which is a by s plus sigma square. S plus sigma within bracket square. That means two roots are there at s equal to sigma, and the order of multiplicity is equal to k. So from Laplace inverse, easily you can say that the term, the response term or terms rather generated by those two roots will be, one will be a1 into e to the power sigma t, and for the second one it will be a2t into e to the power sigma t, isn't it?
Yes, ma'am.
Clear? Clear to everyone? So now we can
Yes.
generalize that the roots of multiplicity k at is equal to sigma. So the generic expression will be a1 plus a2t plus a3t square dot 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 plus akt to the power k minus 1, k minus 1. Since this one is a1 k to the power 0, sorry, t to the power 0. So ak t to the power k minus 1 whole multiplied by e to the power sigma t. Fine. So we have considered simple roots on the real axis, but not on at the origin of the S plane. Next, next possibility is complex conjugate root pair at A is equal to sigma plus minus j omega. Complex conjugate root pair, simple root pair. Okay, without the order of multiplicity is equal to 1. So for this sigma term, since the real part is non-zero, so 1 e to the power sigma t, this term will be there. And for this angular frequency omega, we'll get a term which is sine omega t plus beta. It's basically a generic expression. And please verify each and every one. Write down the transfer function for these root locations, okay, and take the Laplace inverse and find out, verify this response terms. So the response term will be a sine omega t plus beta whole multiplied by e to the power sigma t. এটা হবে তো? Have you understood this?
Yes, ma'am.
Now, the next possibility is complex conjugate root pairs with multiplicity k. That means at this particular location, suppose this is my S plane. So these are the simple complex conjugate root pair. Instead of simple complex conjugate root pair, we are having two root pairs at the same locations. That means four roots. So if you generalize the order of multiplicity to k, then the response term contributed by those roots will be a1 sine omega t plus beta 1 plus a2 t, just like this case. A2 t sine omega t plus beta 2 plus ak t to the power again k minus 1 sine omega t plus beta k whole multiplied by e to the power sigma t, because since the real part is non-zero. Now, so we have considered complex conjugate root pairs as well as real roots. Now, we'll focus on the imaginary axis. The roots of the characteristic equation can appear on the imaginary axis as well. So, complex conjugate root pair at s is equal to plus minus j omega. So, what is the difference between these two? The real
Real
part is zero. Real part is zero. That means the both the roots are on the imaginary axis.
Yes, ma'am.
So since both the roots are on the imaginary axis, so if I compare with this equation, so this sigma will be equal to 0 and hence it will be 1. So the response will be a sine omega t plus beta. Only this part will remain. So a sine omega t plus beta, that means the response term will be an undamped oscillation with amplitude A. Next, again, we'll consider that the roots are appearing at this particular location, plus minus g omega, but multiple roots are appearing at these two locations. That means complex conjugate root pairs with multiplicity k at s equal to plus minus j omega. Multiplicity k. Again, we can compare this two. Since sigma is 0, so this part will be 1, or otherwise we can directly find out by taking Laplace inverse. So the response term will be a1 sine omega t plus beta 1 plus a2 t sine omega t plus beta 2 plus the last term will be ak t to the power k minus 1 sine omega t plus beta k. Now, the last possibility is single root at origin. Single root at origin. That means the transfer function will be a by s. So if we take Laplace inverse, we know that the response term will be a. That means constant amplitude. Constant amplitude. And the last possibility is roots with multiplicity k at origin. Hence, the response term will be a1 plus a2t plus the last component will be ak t to the power k minus 1. টেবিলটা একটু দেখো, দেখো ক্লিয়ার হলো কিনা। Clear? Hmm? Okay. Okay, fine. Now we are discussing where our concern is linear system, right? So it might so happen that in a system there is a root at this particular location, and two other roots are appearing as complex conjugate root pair and are present at this particular location on the S plane. Okay. So the system will be, what will be the order of the system? How many roots are there? How many roots are there? One root at s equal to sigma and two roots at s equal to sigma plus minus g omega. So how many roots are there? Three. So what will be the order of the characteristic equation?
3.
Third.
Three. Third order. Fine. So that means the root can be real, the root can be complex conjugate pair, or any combination of all these possibilities. Any combination. Any combination. Okay. So let's assume for the time being, let's assume that one root is here and other two roots are at this location on S plane, right? So since we are considering a linear system, the response term will be this one plus this one, as the law of superposition will hold. So this term, the response terms can be added, isn't it? So for this root, the response term or response generated by the system, exhibited by the system, will be this. And because of these two roots, because of these two roots, the response term, the second component of the response will be this one, isn't it? So because of the law of superpositions, if we have any combinations of these possibilities, then we can add the corresponding or respective response terms. Now, let's first focus on this first four cases where the real part is not zero. The sigma part is not zero. So in each of this response term, you see there is a term which is e to the power sigma t, right? So sigma is positive, if sigma is positive, then what will happen? As time t tends to infinity, as time t increases, this response term or this response term or this one will go on increasing,
Yes.
and as t tends to infinity, the response terms will be infinite or completely unbounded,
Yes, ma'am.
right? So
Unstable system.
yes, unstable. And why unstable? Because sigma is positive, and sigma positive signifies that you draw on your own, draw the S plane. Sigma part positive means the roots are appearing on the right half of the S plane. The imaginary axis actually divides the S plane into two halves.
Yes.
One is for sigma less than 0, will get the entire left half of the spline. Second. So this is my spline. This is my spline, and this is the imaginary axis. This imaginary axis, actually, if I just consider this imaginary axis, This imaginary axis actually divides the S plane into two halves. One is this half, the other one is this half. So this half is called left half of the S plane, where the sigma value is always less than 0. And this one is known as the or called as the right half of the S plane, where the sigma value is positive, isn't it? This is
Yes.
this is the positive real axis, and this is the negative real axis. Negative real axis. So this is the right half of the S plane. Let's go back to that particular table. So if sigma is positive, then the system response will be completely unbounded. That means if the roots of the characteristic equation, or if the locations of the closed loop poles on the S plane are on the right half of the S plane, then the system will be unstable. And if sigma is negative, you see, as time t tends to infinity, all these terms will vanish to zero, will decay down to zero. Do you agree?
Yes, ma'am.
That means if the roots of the characteristic equations are located in the left half of the S plane, then the system will be asymptotically stable as the response terms are decaying down to zero as t tends to infinity. So what is the conclusion? If the roots are lying on the right half of the S plane, the system will be unstable. And if the roots are in the roots means the roots of the characteristic equations are in the left half of the S plane, then the system will be asymptotically stable. Okay. Now let's consider that this this combination, one real root, one complex conjugate root pair. So the response term will be this one plus this one plus this one, right? Now, if you consider that the complex conjugate root pair are lying on the left half of the S plane, that means this sigma value is negative. Whereas the simple root is lying on the right half of the S plane, in the right half of the S plane. So since this sigma is negative, that means this term, which is present in the response of the system, okay, this term will decay down to zero as t tends to zero. Do you agree?
Yes, ma'am.
But one single root of the system, or one single closed loop pole of the system, is lying in the right half of the S plane, and because of the presence of this term at the output of the system, as t tends to infinity, the output will gradually increase, and as t tends to infinity, the output will be unbounded,
Yes, ma'am.
right? So from this example, what we can conclude, suppose for an nth order system, if n minus one number of roots are lying in the left half of the S plane, and one single root is lying in the right half of the S plane, because of the presence of that one single root at the right half of the S plane, the system will be unstable. Do I have to repeat? Do I have to
Yes.
repeat? Hmm?
Yes, ma'am.
Suppose we are considering an, have you understood the previous example?
Yes,
Yes.
ma'am.
Right? So now we are trying to generalize that. Suppose we are considering an nth order system. So how many roots will be there? N number of roots or
Yes,
n
ma'am.
number of closed loop poles? Now let us
Yes.
assume that n minus 1 number of roots are lying in the left half of the spline. But one single root is lying in the right half of the spline, like this one single root. So the response terms contributed by those n minus 1 roots located in the left half of the spline will decay down to 0 as t tends to infinity.
Yes.
Yes or no? Yes or no?
Yes, ma'am.
Are you convinced?
Yes, ma'am.
Do you agree? Now, one single root is there in the right half of the spline. Because of the presence of one single root at the right half of the spline, the output response will have this term as well, which will go on increasing further and further with t. And as t tends to infinity, this term will be unbounded, isn't it?
Yes, ma'am.
So, what is the conclusion? Because of the presence of one single root in the right half of the spline, the system will be unstable because of this particular term,
Yes, ma'am.
right? So, for a system to be stable, asymptotically stable, to be asymptotically stable, it is required that all the roots of the characteristic equation should lie in the left half of the S plane. Or in other words, for a system to be stable or to be asymptotically stable, all the closed loop poles of the system should be located in the left half of the S plane. Clear?
Yes, ma'am.
Yes, ma'am.
The second part is, even even if one single root is there in the right half of the S-plane, while the rest are in the left half of the S-plane, the system will be unstable. So, have you understood the second part?
Yes, ma'am.
Now, so complex conjugate root pair on imaginary axis. On imaginary axis. So this will be the term contributed, response term contributed by these roots. So, and as I said, this is undamped oscillation with finite amplitude. So from our earlier discussions, we can conclude that if such roots are present in the system will be limitedly stable. You remember we have discussed stable, unstable, limitedly or marginally stable systems.
Yes, ma'am.
At the output, we are getting undamped oscillations with finite amplitude. So if we can tolerate this undamped oscillation, then we can work with that particular system, right? And if we can't tolerate, then we'll not be able to work with that particular system. So accordingly, the system will be considered as a, or will be treated as stable or unstable. So in general, we call the system as limitedly stable one. Now, complex conjugate root pairs with multiplicity. So this is the response term contributed by those response terms contributed by those roots. So you see a1 sine omega t plus beta 1, but the second term is a2 t, and the last term is ak tk minus 1. So as t tends to infinity, what will happen? The output of the system will be infinite, or in other words, will be completely unbounded. And hence the system will be unstable. So if on the imaginary axis we have conjugate root pairs with multiplicity greater than 1, with multiplicity equal to 1, limitedly stable, but multiplicity greater than 1, a greater than 1, then the system will be unstable as the response will go on increasing with time. Clear?
Yes, ma'am.
And last two cases, single root at origin, a by s, a by s. Are you familiar with this particular transfer function, 1 by s? Have you ever come across this kind of transfer function, 1 by s? What kind of device it signifies?
Unit step.
The transfer function of the system, I'm
Integrator
not
circuit.
talking integrator, right? That is the transfer function of the system. A by s is the transfer function of the system, single root at origin. So the transfer function of the system is a by s. So what kind of a system it is? I'm not talking about the input. Am I clear? So this is basically signifies a integrator circuit. Clear?
Yes, ma'am.
Okay. So the response term will be A, that means constant amplitude. Again, if you can tolerate this constant amplitude at the output, the system, you can work with that particular system. And if you can't tolerate, you will not be able to work with that particular system. And in general, we call this type of systems as limitedly stable or marginally stable systems, isn't it? So in this cases, in these two cases, we'll get marginally stable systems. And roots with multiplicity k at origin, a by s squared, that is the transfer function of the system, a by s squared, that means double integrator, isn't it?
Yes.
Double integrator, a by s squared. So the response term will be a1 plus a2t, and if we generalize the order of multiplicity as k, so the response term is given. So from this expression, it's clear that again the system will be unstable as the response term is increasing as t is as time is increasing, time progresses, and when t tends to infinity, the response term will be unbounded. So in this four cases, actually we are not getting a perfectly stable system, an asymptotically stable system. So if simple roots are there on the imaginary axis, simple root at origin or simple complex conjugate root pair on imaginary axis, then the system will be at best a limitedly stable one, a limitedly stable one. And if the multiple roots are located on the imaginary axis, then from this expression and from this expression, it's clear that the system will be unstable. Are these conclusions clear?
Yes, ma'am.
Again, for an nth order system, n number of roots will be there. So let's assume that n minus 1 roots are there in the left half of the S plane. N minus 1 roots are there in the left half of the S plane. So those roots will contribute response terms which will decay down to 0 as t tends to infinity.
Yes, ma'am.
And suppose one single root is there at the origin. Single root is there. So for this particular root, this response term will be generated, right? So it will remain present. So though n minus 1 roots are there in the left half of the S plane, because of the presence of a single root at origin, the system will be ultimately a limitedly stable one. Have you understood? Similarly, if n minus 2 roots are there in the left half of the S plane and 2 roots are there on the imaginary axis at plus minus j omega, then at the output, ultimately as t tends to infinity, we'll get a sustained oscillation with finite amplitude. Okay. So under that particular situation, the system will be limitedly stable. The system will not be an asymptotically stable one. Okay. And if n minus 2 roots are there in the left half of the S plane and 2 roots are there at the origin, 2 roots are there at origin on the S plane, origin of the S plane, right? So what will happen? N minus 2 roots will contribute terms which will decay down to 0 as t tends to infinity. But because of the presence of 2 roots at the origin, the response term uh, will be a1 plus a2t, and hence the system will be unstable. Clear?
Yes, ma'am.
Do you have any query? Is it absolutely clear? Or okay. Note the roots of the characteristic equation of a system may be both real and or complex conjugate or conjugate along with multiplicity of various order. So very fast I'm going through this. Already we have discussed all these things. The conclusions are all the roots which have non-zero real parts, namely cases 1, 2, 3, and 4, contribute response terms containing e to the power sigma t term. You have seen that. If sigma less than 0, that is the roots lie in the left half of the S plane, LHS in short, then CDT or CT will tend to 0 as t tends to infinity. And however, if sigma greater than 0, the roots will lie in the right half of the S plane and CDT will increase without bounds. Roots on the j omega axis with multiplicity, that means cases 6 and 8 will also tend to infinity as t tends to infinity. Single root at origin or simple conjugate roots on imaginary axis contribute response terms which are either constant amplitude or constant amplitude oscillations. So we sum up, and our final conclusion is number one, if all the roots of the characteristic equation describing an linear time invariant system have negative real parts, that means the roots are lying in the left half of the S plane, then the impulse response. Why this term impulse response? Because response, we have assumed that the response to the system is impulse one, unit impulse. So impulse response is bounded and eventually decreases to zero as t tends to infinity. T tends to infinity. So the system is asymptotically stable, and since we are considering linear system, hence the system will be BIBO stable, bounded input, bounded output stable. Just go through this point, and if this point is clear, is this point is clear?
Yes, ma'am.
Second one, even if a single root of the characteristic equation has a positive real part, that is, even if a single root of the characteristic equation is in the right half of the S-plane, while the rest of the roots are in the left of the S-plane, sorry, then the impulse response of the system is unbounded. If only one single root is there in the right half of the S-plane, the system will be unbound, output response will be unbounded, and the system will be unstable. Point number three, if the characteristic equation has repeated roots on the imaginary axis or j omega axis, the impulse response of the system is unbounded. Hence, the system is unstable. Already we have discussed all these things at length. And the last one, if one or more non-repeated roots of the characteristic equation are on the j omega axis, that means simple roots on j omega axis, imaginary axis, then the system may be termed as limitedly stable or marginally stable. Right, page number 11, where we have defined limitedly or stable or marginally stable system. Clear? Have you understood? Do you have any doubt?
No, ma'am.
So already we know that if an LTI system is BIBO stable, then it will also be asymptotically stable. Or, in other words, if an LTI system is asymptotically stable, then it will be BIBO stable as well. But this is not true for nonlinear systems. Now, what was our basic assumption? Basic assumption was the input to the system is unit impulse. Why? We have gone for that particular assumption because the Laplace transform of unit impulse is equal to 1, right? And our basic assumption was, and that can be proved as well, that the output response of the system of a linear system does not depend upon the nature of the system. If a linear system is stable for unit impulse, it will be stable for unit step as well, or unit ramp, etc. Fine. But at that point of time, we said that there is one exception. So what is that exception? That we'll discuss. So this exception is this phenomenon is known as instability due to resonance. Instability due to resonance. Now I'll explain instability due to resonance later on. First of all, to make it simple, let's consider one example. Then the concept will be very clear. Suppose this is the transfer function of the system. Ts, closed loop transfer function of the system, Ts is equal to 4 by S into S plus 4. Right? Now, that means this is Cs by Rs. You take a note it down. Cs by Rs will be 4 by S into S plus 4. Now, suppose we excite this particular system with unit step. So under that particular situation, Rs will be 1 by S লিখছো তোমরা?
Yes, ma'am.
1 by S, right? So Ts is equal to Cs by Rs, or Cs, we are interested about Ct, right? Time response of the system. So Cs will be 4 by S into S plus 4 into 1 by S.
Yes.
So Cs will be 4 by S square plus S square into S plus 4.
Yes.
So in CT, because of the presence of this term S square, what will happen? The CT will have a component which will be equal to A1 plus A2T, isn't it? And obviously there will be a third term which is A3 plus e to the power minus 40. Clear?
Yes, ma'am.
Absolutely clear? So three terms will be there. One is A1T, one is A1 plus A2T plus some A3 e to the power minus 4T. So because of the presence of that A2T term, Ct will be unbounded at t tends to infinity. Do it
Yes,
on
ma'am.
your own. Ct will be unbounded, right? And under that particular situation, the system will be unstable. The system will be unstable.
Yes.
Yes. So here we can say that one root is there in the right half of the S plane, and one root is there at the origin. So the system would have been limitedly stable. But since the input is Rs, unit step, this input is making the system unstable. If the input is a unit impulse, then the system will be limitedly stable. But since the input is unit step, because of this particular input, because of the nature of the input, which is unit step, the system will be unstable, right? Now the Laplace transform of unit step, as I said, is 1 by S. So the the input is having input. Remember the input. The input is having a pole at S equal to 0. The input is having a pole at S equal to 0. Yes or no? The input is 1 by S in the
Yes,
transform
ma'am.
domain. So input is having a pole at S equal to 0.
Yes,
That
ma'am.
means having a pole on the imaginary axis, and that pole is matching, or that pole is basically present as a pole in the transfer function of the system on the imaginary axis, right? So that pole on the imaginary axis of the input is matches with a pole of the simple pole of the transfer function of the system, and the simple pole is lying on the imaginary axis. So the input pole on the imaginary axis, input simple pole on the imaginary axis matches with a pole, simple pole of the system, which is also on the imaginary axis. Is the situation clear? Absolutely clear?
Yes, ma'am.
Because of this match, and fine, already we have seen the system is unstable because of this unit step input. So this kind of instability is called instability due to resonance. Instability due to resonance. So let's see. So at times, the stability of an LTI system may depend on the input. This phenomenon where the stability of an LTI system indeed depends on the input is known as instability due to resonance. So this phenomenon may occur when a simple system pole. This phenomenon may occur when a simple system pole without having any multiplicity, simple system pole appears on the imaginary axis. If in such a system an input is applied, acha, okay, come to this one. An input is applied which has a pole that matches with one of the simple system poles on the imaginary axis, the output response of the system will become unbounded. বুঝা গেল না আমি আরেকবার so instability due to resonance. A system is having a simple pole on the imaginary axis, and in such a system we are applying an input which has a pole that matches with one of the simple system poles on the imaginary axis. Then obviously the output response of the system will become unbounded, that we have already seen. Clear?
Yes, ma'am.
Yes, ma'am.
So this is known as resonance phenomenon. And this kind of instability is known as instability due to resonance. So these are the simple assignments, and you should solve this. The second case is, you'll have to solve this. Find the response of the system given by the closed loop, this one is given by the closed loop transfer function as Ts is equal to 1 by s plus 2 and s squared plus 1. That means simple conjugate pair on imaginary axis at s is equal to plus minus root 1, plus minus j, right?
Yes, ma'am.
Simple conjugate pair. So if we excite that particular system with a sinusoidal input, which is given as Rt is equal to sine t, Rt is equal to sine t. So what will be RS? 1 by S square plus 1,
1 by
S square plus 1, right? So naturally CS will be 1 by S plus 2 into S square plus 1 whole square, and find out the response term and comment on the stability of the system. That is your assignment. Clear?
Yes, ma'am.
So from our discussions, with the help of this imaginary axis, we can divide the complete S-plane into two halves. One is left half, the other one is right half. If all the roots are confined in the left half of the S-plane, obviously excluding the j omega axis, that is the demarcating line, the system will be asymptotically stable, and even one single root is there in the right half of the S-plane, or one single closed loop pole is there in the right half of the S-plane, the system will be always unstable. And if the roots are appearing on the imaginary axis, then either the system will be limitedly stable, or if the roots are there on the imaginary axis with multiplicity greater than 1, then the system will be unstable. And if the system is limitedly stable, then we can say the system is non-asymptotically. If we can tolerate that amount of deviation, then we can say that the system is non-asymptotically stable. So I have prepared a chart. I don't know how much legible is this one. So the first case, locations of the closed loop poles and stability of a system. Locations of the closed loop poles means locations of the closed loop poles on the S plane, and the stability of the system. So the first case is all the system's poles are in left half of the S plane. So now we know that under this particular situation, if all the poles of the system lie in the left half of the S plane, the system will be asymptotically stable. Asymptotically stable. In contrast, only one single pole lies in the right half of the S plane, while the rest are in the left half of the S plane. Left half of the S plane means excluding the imaginary axis. So because of this one single pole lying in the right half of the S plane, the system will be unstable. The system will be unstable. Now we are focusing on the imaginary axis, left half, right half, imaginary axis. Some of the system poles are on the imaginary axis and the rest are certainly in the left half of the S-plane. Right? Because we know that if one single pole is in the right half of the S-plane, the system will be unstable. So some of the system poles are on the imaginary axis and the rest are in the left half of the S-plane. Now this situation can be viewed in this manner. At least one of the system poles are repeated in nature. That means one of the system poles means system poles which are lying on the imaginary axis, and rest are lying in the left half of the S-plane. So at least one of the system poles on the imaginary axis are repeated in nature. So we know that the system will be unstable, isn't it? Yes or no?
Yes, ma'am.
System will be unstable. At least one of the system pole on the imaginary axis. Remember, the rest are lying in the left half of the S-plane. So at least one of the system poles on the imaginary axis is present in the form of pole in RS, that means in the input, in the form of pole in the input. So what will be the conclusion? The system will be unstable, and the system will be unstable because of the presence of the system pole as a pole in the input. So this is known as instability due to resonance. And the third one is all the poles on the imaginary axis are simple, that is without having any multiplicity, rest are in the left half of the S-plane, and none of these poles on the imaginary axis are present in the input. None of these poles on the imaginary axis, none of the simple poles on the imaginary axis are present in the input. So the system will be limitedly stable. To be precise, this system will be called a limitedly stable or a marginally stable one, or in other words, we can call it a non-asymptotically stable system. Better to note that, first of all, we'll classify this kind of system as limitedly stable, right? And in some specific cases, we can call the systems as non-asymptotically stable. Just go through this page and find whether you have understood or not. Is it absolutely clear or not? Is it clear? Should I proceed? Is it clear? Have you understood? Should I proceed? So these are some diagrams. The simple root is lying in the left half of the S-plane. So the output response will decay down to 0 as it tends to infinity. The simple root is lying in the right half of the S-plane on the positive real axis. Hence the output response is increasing asymptotically. Sorry, increasing exponentially, and it will be unbounded as it tends to infinity. Complex conjugate root pair in the left half of this plane. So damped oscillations, and the oscillation will die down. Right half of this plane. So that is the nature of the input. The oscillations are going on increasing, and ultimately the system will be unstable. Conjugate pair on the imaginary axis, undamped oscillation. So double roots, conjugate pairs with multiplicity 2. So the output response is increasing. System unstable at origin, constant amplitude, double root, it's increasing. A1 plus A2T. Already we have discussed this. Positive real part, unstable, negative real part, stable, and on the imaginary axis, simple, then limitedly stable. Okay, absolutely stable system. Though in this particular chapter, we'll use the term absolutely stable. I'll define what is meant by absolutely stable later on. So generally, absolutely stable, a system is said to be absolutely stable with respect to the parameter of the system. So parameters means the parameters of the system are reflected in the coefficients of the characteristic equation or coefficients of the transfer function, isn't it? Yes or no? And conditionally stable with respect to a parameter if the system is stable for a certain bounded ranges of values of this parameter. Suppose a parameter A of a system is within a limit A1 to A2. If it varies from A1 to A2, the system is stable, and if it increases or if it if the value of A changes beyond A2 or uh, moves below A1 and the system becomes unstable, then the system is said to be conditionally stable. Conditionally stable with respect to that particular parameter A of the system. So already we have seen this particular diagram. So relative stability. In this particular chapter, we'll not discuss what is relative stability. Relative stability is basically a concept of stability which can be quantified. We'll discuss relative stability at length while we'll be discussing Nyquist stability criteria. So let's come to this section, necessary conditions for stability. Necessary conditions. So what are the necessary conditions for stability? Actually, why are we going for this necessary conditions? Because if the order of the system is beyond third order, then to find out whether the system is stable or not, what we'll have to do? We'll have to factorize the characteristic equation of the system. So if the order of the system is fourth order, if the order of the system is 4 or 5, then the order of the characteristic equation will be of the order 4 or 5. And to find out the locations of the roots of the characteristic equation, because already we have studied that if we know the locations of the roots of the characteristic equation on the S plane, then from that particular information we can conclude about the stability of the system. But for a higher order system, to find out the locations of the roots of the characteristic equation on the S plane, we'll have to solve a higher order equation, a fourth order equation or a fifth order equation, and the method is very time consuming and cumbersome one. right? So for that, without finding out the roots of the characteristic equation or solving the characteristic equation, can we can we judge the stability of the system? Can we judge the stability of the system? That means what kind of stability we are concerned about. We are trying to find out the answer to the question whether the system is stable or not. Am I clear? So what is the question? The question is whether the system is stable or unstable. We are not phrasing our question like whether the system is stable for certain value of the parameter, for certain parameter of the system. No, our question is very straightforward, whether the system is stable or not. So the answer to this particular question is basically the notion of or definition of absolute stability. Absolute stability. So what is absolute stability? What is the notion of absolute stability? Absolute stability is basically one yes no criterion. Yes no criterion. Either the system will be stable or the system will be unstable. That is basically the absolute stability of the or notion of the absolute stability of a system. Here
Yes, ma'am.
we are not quantifying, we are not making it complicated. Simply we are asking whether the system is stable or not. So necessary conditions for stability. Only necessary, not sufficient. Necessary conditions for stability. So certain conclusions regarding the stability of system can be drawn merely inspecting, by simply inspecting the characteristic equation, or rather inspecting the coefficients of the characteristic equation. And the characteristic equation is in the polynomial form. Will not we don't need to factorize the polynomial. Okay. So the characteristic equation is expressed in polynomial form. In that case, simply inspecting the coefficient, that means a0, a1, a2, an, the coefficient, we can come to certain conclusions. What is that? All the coefficients, the necessary conditions for stability is all the coefficients of its characteristic equation QS equal to 0 should be real. Should be real, should have the same sign, and none of them should be 0. These three are the necessary conditions for the absolute stability, for ascertaining the absolute stability of a system. Clear? So QS is equal to, QS can be represented as A0 is to the power n, A1 is to the power n minus 1, an minus 1 is an. So we'll inspect A0, A1, an minus 1, an. And without any loss of generality, if you assume that A0 is greater than 0, A0 is greater than 0. If that is not the case, then we can multiply this by minus 1 and make A0 positive. Isn't it? Yes or no? Hello, are you present?
Yes, ma'am.
হুম? তো বুঝতে পারছি না। তোমাদের সিস্টেমের তোমাদের এন্ড থেকে তো কোনো রেসপন্স নেই মাঝে মধ্যে। আচ্ছা, so a0 greater than 0, if a0 greater than 0, then the first condition is all these coefficients a0, a1, a2, an minus 1, an, all these coefficients should be positive. That means they should bear the same sign. They should have same sign. None of them should be 0. So if we get a characteristic equation which is a0 s to the power n plus a2 s to the power n minus 2, a1 is 0. That means this term is missing. this term is missing. Hmm. Then the necessary condition will be violated and the system will be unstable. So none of the coefficient should be zero. None of the coefficient should be zero. And the third one is the all the coefficients should be real. So the first one is very simple. Why all the coefficients should be real? Because we know that the roots of the characteristic equations can be real or complex conjugate pair with different order of multiplicities. Yes or no?
Yes, ma'am.
So if you
Yes, ma'am.
multiply the real roots, obviously s plus 3 into s plus 2 into s plus 1, obviously all the coefficients will be real.
Yes.
and
Yes, ma'am.
and if we assume that, okay, fine, complex conjugate root pairs are present, then again when we multiply, the coefficients will be real. Yes or no? Right? So that's why, since the roots can be either real or complex conjugate pair, so the coefficients will always be real, have the same sign. I'll come to that. And none of them should be zero. None of them should be zero. Very simple. If n is zero, this coefficient is zero. So what will be the characteristic equation? It will be a0 s to the power n plus a1 s to the power n minus 1 plus a n minus 1 s equal to 0, since an is 0.
Yes.
So one root is there on the imaginary axis on the origin of the s plane.
Yes, ma'am.
So that means the system can be at best limitedly stable, but the system is not absolutely stable. No. Clear? So these are the necessary conditions, and we'll inspect this coefficients, and if I found that some coefficients or one of the coefficient is missing, then and then we'll conclude that the system cannot be a stable one. If one coefficient is negative while the rest are positive, or one or two coefficients are negative, okay, that means if all the coefficients are not of same sign, then and then we'll conclude that the system is unstable. Now, the characteristic equation can be written in this form: Qs is equal to A0, this is product of S plus sigma k's, where sigma k's are the real roots. Can you follow this? Into
Yes, sir.
product of
Yes, ma'am.
complex conjugate root pairs. That means S plus sigma L square plus omega L square. So here L is varying from 1 to 2, whatever, and here K is varying from 1 to 3, whatever, depending on the order of the system. So this equation can also be expressed in this form, right? Now, for some sigma k, if the sigma k or some real root is located in the right half of the S plane, then that particular factor, because of that particular root which is lying in the right half of the S plane, that particular factor will be S minus some sigma k,
Yes, ma'am.
right? So that negative or minus sign, when we'll multiply all these terms, this minus term may get reflected in one of these coefficients.
Yes, ma'am.
Have you understood? So if one root is there in the right half of the S plane, one of these coefficients may have a negative sign. One of these coefficients may be less than 0. Maybe. Because we are discussing necessary conditions, not sufficient. I'll come to that. Similarly, if some sigma L is 0, if some sigma L is 0, for some L, if one sigma L is 0, so what will happen? This term will boil down to S square plus omega L square. So one conjugate root pair on imaginary axis.
Yes, ma'am.
Right? That means the system is not absolutely stable.
No.
And one term will be missing. If sigma L is 0, sigma L is 0, sigma L is not 0, then if I expand this term, it will be S square plus sigma L square plus twice S sigma L, twice S sigma L, twice S sigma L,
Yes, ma'am.
right? So if sigma L is 0, that twice S part will vanish.
Yes.
And because of the absence of that twice S term, it might so happen that one of the coefficient will be 0 in this particular expression after multiplication.
Yes, ma'am.
So that's why those sorry, just the necessary conditions have been enumerated. Now the necessary conditions, and if sigma k is 0, 1 sigma k is 0, then it's clear that 1 sigma k is 0. That means there will be a root at origin of the S-plane. That means an will be 0. An will be 0. Abe to? Fine. Now, these necessary conditions are both necessary and sufficient for first and second order system. First and second order system. So, for the first order system, if you follow that particular convention, the transfer function, or the characteristic equation of the first order system is A0S plus A1. And since it's a first order system, one single root will exist, or one single closed loop pole will be there for that particular system. And the location of the pole on the S plane is S1 is equal to minus A1 by A0.
Yes, ma'am.
So if A1 and A0 bear same sign, then obviously the root will lie in the left half of the S plane, making the system stable.
Yes, ma'am.
Right? So for first order system, the necessary conditions are sufficient. If A1 is 0, then there is a root at origin and the system is not absolutely stable. So the first order system, we have examined that the necessary conditions are sufficient conditions as well. For second order system, this is the transfer function A0S square. Is it legible?
Yes, ma'am.
Okay. A0S square plus A1S plus A2 equal to 0. So since this is a second order system, so two roots will be there, S1, S2, which is equal to minus A1, that you know, plus minus, just go through this expression. You know it. So easily you can verify that if A0, A1 and A2, A0, A1 and A2 bear the same sign, then the roots will be located at the left half of the S-plane, isn't it? Are the two negative distinct real root or two negative identical real root? Do you agree?
Yes, ma'am.
Okay, fine. Okay. Now, this necessary conditions are not sufficient condition for third order system. Third order and for higher order system. Only necessary conditions are sufficient conditions for first and second order systems. So let's take one example. One example is given over here. S cube, you see all the coefficients are present. 1, 1, 2, 8. So all the coefficients are present, as well as all the coefficients are bearing same signs. And obviously all the coefficients are real. So if you solve this equation, I guess you will be able to solve this equation since this is a third order system. With the help of your calculator, I guess you'll be able to solve this equation, right? You solve this
Yes, ma'am.
equation and you'll find that one real root is there, s plus 2, just verify this. One real root is there and this 2 you see. So what is the location of this complex conjugate root pair? Complex conjugate root pair. What is the locations of this complex conjugate root pairs? On the
Right
S
half.
plane? On the S plane. On the S.
Left half of this.
Right.
Complex conjugate
Uh,
root pair.
so right half of this.
Are you sure, right or left?
Right of the S plane.
Right,
Right.
right.
Minus. Here is a minus sign, right? So the
Real part
roots
is
are,
right half.
yes, the roots
Up
are
करें then go करें.
roots are 0.5 plus minus j root 15 by 2, isn't it?
Yes, ma'am.
Roots are plus 0.5 plus 0.5.
Yes,
Okay,
ma'am.
so that means the real root is lying in the left half of the S plane, but the real part of the complex conjugate root pair is not negative. The sigma part of the complex conjugate root pair is not negative, it's positive.
Yes.
So for higher order system, here, the positiveness of the coefficients, all the coefficients are present and all the coefficients are positive. The positiveness of the coefficients of the characteristic equation ensures the negativeness of the real roots. The real root is lying in the left half of this plane. So the negativeness of the real roots, but does not ensure the negativeness of the real parts of the complex roots for third and higher order system. Is it clear? Does not ensure, does not guarantee. The negativeness, you see, the real part for the complex conjugate root pair is positive. So does not guarantee, does not ensure the negativeness of the real parts of the complex roots for third and higher order systems. Right? So these conditions cannot be sufficient conditions for third and higher order system. Have you understood?
Yes, ma'am.
Yes,
So
ma'am.
how to judge the stability of a higher order system? So we need to solve the characteristic equation, find out the locations of the roots of the characteristic equation on the S plane to judge the absolute stability of the system. No, it's, as I said, it will be a very time consuming, cumbersome method. So for that, we'll discuss two stability criterion. One is Raoult stability criterion and the other one is Harvard stability criterion. And those two criteria helps us to judge the absolute stability of higher order systems. Any question?
No,
Can I
ma'am.
stop sharing?
Yes, ma'am.
Okay. So, do you have any question? In the next class, I'll start route stability criterion. Any
Okay,
doubt
ma'am.
or any question?
ম্যাম এই যে রেসপন্স গুলো হচ্ছিল ম্যাম, ওগুলো ইম্পালস রেসপন্স, যদি স্যার ম্যাম এগুলোর ক্ষেত্রে যদি স্টেপ বা অন্য কিছু ইনপুট দেওয়া যায় তাহলে তো ম্যাম
অ্যাকর্ডিংলি সেটাকে ফলো করবে।
হ্যাঁ, তো তাহলে এই যে স্টেবিলিটি গুলো চেক করছিলাম যে শুধু এসএস গুলো সিগমা, সেটা তো স্যার এই এই টু দি পাওয়ার সিগমা, এটা তো শুধুমাত্র ইম্পালসের ক্ষেত্রে, বাট এখানে যদি স্টেপ হয় তাহলে তো এই রেসপন্সটা টাইম রেসপন্স সেম হবে না, তাহলে যে এটা স্টেবল মানে হচ্ছেই মানে।
না না, যদি if a linear system is stable for impulse input,
আচ্ছা,
forget about the case instability due to resonance.
ওকে ওকে, আচ্ছা
If there is no uh, closed loop pole on the imaginary axis, that
ওকে,
means the system is asymptotically stable, all the roots are lying in the left half of the S plane,
হ্যাঁ এক্সপ্লেন,
all the roots are lying in the left half of the S plane. Under that particular situation, the system will be stable for any kind of input.
ও ওকে, it is only applicable for linear system that,
It's only applicable, it's only applicable for linear system.
okay
Linear system. It's not valid for non-linear system. It's not
okay
at all valid for non-linear system.
okay, that means if there is no resonance it will be stable for unit
If no
impulse or
poles are there, no poles are there, if the system is asymptotically stable, okay, so
okay
the impulse response will be bounded, the step response will be bounded.
okay okay ma'am. Understood. Thank you.
Okay.